In this last block of the lecture, what we will see are different kind of experimental designs that we can, how we can approach these from a statistical point of view. So one of them is this factorial design. So in factorial design, we will have factors, and for each one of the factors we will have different levels, and the combination of the levels of the different factors will give some response. So for instance, let's say that we want to make the best cake in town, so we can have different factors that are the temperature in the oven, the amount of sugar, the amount of flour, the amount of eggs, and then you have different levels for this one, so you can have different temperatures, different amounts of sugar, and you can make combinations of these, and for each one of them you will have a cake, and then you will have to characterize numerically this cake in terms of taste, color, consistency, or whatever, and then you can try to find the best combination that produces the best result. And another kind of design is this one, this completely randomized design. So this is the simplest design. Each experimental unit is assigned to a treatment at random, and without taking into account any of the individual characteristics. And this is good when you have homogeneous experimental units, and it can tolerate an equal number of so that the groups doesn't need to be balanced, but it is better if they are balanced, because then the comparisons will have better variances. But they may have a problem. So for instance, here let's say that this is the order also in time in which you will do the experiments, and let's say that you're doing some kind of surgery that you are not too proficient at the beginning, but after doing all this kind of, so you apply different treatments. For each one of them you extract, I don't know, the liver of the animal, and then you make some measurement on the liver. So for instance, at the beginning you don't extract the liver very well, but at the end you do it very well, and you see that just by chance these purple treatments have tended they tend to be concentrated towards the end, so the measurements that you will have from the purple will be different from the measurements from the gray, but not because of the treatment, but because your skill has increased. So you may break this time dependence, and you may make blocks. So then within block 1 you will apply the 4 treatments at random, and then you have time block 2, and again at random, and so on. So if there is a difference between so if your skill is improving, then you will wash out this difference by applying all treatments in all blocks. And you can use blocks to block space, or to block time, or to block space, or to block the liter, or to block sex, age, or whatever. So this is a very much used kind of design. And then you have match pair designs. So match pair is you would like to make blocks, but these homogeneous, you cannot have exactly homogeneous groups, but you try to make them as homogeneous as possible. So for instance, let's say that you are interested in seeing what is the reaction time of people when they sleep 2 hours only or 10 hours. And then you will have 10 students in group 1, in group A, 10 students in group B. But the problem is that some people constitutively, by default, they need to sleep less, while some other people need to sleep more. So if for by chance some of these people that need to sleep more tend to gather here in this group, then the differences that you're observing is not because of sleeping more or less, but because particularly these people are sleeping very little and they need to sleep much more, so they are really tired. So there is this confounding of what is the constitutively amount of time that they need to sleep with the treatment, that is how much they sleep for this particular experiment. So what you can try is to match people by all factors that you think that can make them more homogeneous. So for instance, you can match for age, for gender, for normal sleeping length. So you find for every person in group A, you find which is the most similar person, and then you assign that person to group B. And then once you have the groups A and B, now you randomly assign to treatment or control. So first you find the pairs and then you assign randomly to the treatment. We have also already seen these crossover designs. So a crossover design is a way of blocking time or also blocking the animal. So for instance, let's say that you are analyzing a kind of treatment that doesn't modify the animal. So you can apply the 3 treatments in a row. So you can apply to animal 1 treatment, the red treatment, then you leave a washout period, and then there is no effect of treatment of the red treatment on the animal anymore, and now you apply a new treatment, then you leave a washout period, a new treatment, and then the variability between animals you are removing because you have applied to the same animal all treatments. So now the animal is a block, and you can also do it, for instance, if in different parts of the animals. So you can use 3 different regions in the skin, and you have to make sure that the treatment you are applying is not systemic, so that they don't crosstalk. So the green treatment doesn't diffuse somehow to this region. And yeah, so you can use if you can use a crossover design, you will save a lot of animals, and you will also reduce a lot the variability of observations, because you have removed the interindividual variability. And Latin squares is another kind of design in which you want to block 2 variables. So for instance, let's say that you are interested in what is the manufacturing time using some kind of procedure. So you have 4 different procedures, A, B, C, D, but the manufacturing time is not only affected by the procedure, but it is also affected by the machine. So if you use 4 different machines, the same procedure, the machines may respond differently, and they have different manufacturing times. And the same for the operator. So you have 4 treatments, A, B, C, D, 4 machines, 4 operators. So you can construct a Latin square. So you see that each machine is seeing the 4 treatments, the 4 procedures, and in a different order. And the same for the operators. So this is kind of Sudoku. And with this Sudoku, you can identify which is the contribution of the machine, which is the contribution of the operator, and you can separate those contributions from the contributions of the procedure. And factorial designs, this is the example of the oven, and there are a special kind of factorial designs in which the factors only have 2 levels. So let's say that you have factor A, factor B. For each one of the factors you have 2 possibilities that we will identify here as plus and minus. So you have A plus, A minus, B minus, B plus, and so on. And you may have more than 2 factors. And if you perform all combinations, then you are doing a full factorial design. but it is not necessary to do the full factorial. So especially this is very important if you have many factors, so you can do only a fraction of the factorial design. It is not any fraction is valid, but so not any subset of combinations is valid, but you can have, for instance, the number of experiments. So here for 3 factors and 2 levels per factor, you have 8 combinations. You would have to do 8 experiments here, while here with only 4 you are able to identify already the effects of the main variables. You have these split plot designs. It is a factorial design in which one of the factors or some of the factors are easy to change and some other factors are not. So these hard to change factors are assigned to a whole plot. So for instance here, this is A is hard to change, but B and C are easy to change. So A acts as a kind of block, and then within A you modify, you make all combinations of B and C. So you do B1 C1, B2 C2, B2 C1, and so on. And you have also these repeated measures designs. These are experiments in which you measure, you apply the treatment once, but you measure multiple times. So for instance, you apply the treatment and then you measure at 0 time, at 24 hours after the treatment, at 48 hours after the treatment. So you have a lot of measurements, but only one treatment per groups of 3 measurements in the example. So there are ways, specific ways of analyzing this, and the person itself, or the individual, the animal, makes as a block in which you have 3 measurements, and you can identify which is the contribution of that animal. And you have also hierarchical designs. So hierarchical designs are experiments in which you apply the treatment, let's say, to the animals, and then you take the liver, you split the liver in 3 parts, and for each one of the parts you split into 2 aliquots, and then you measure the activity of whatever. So all these measurements at this level, they are called technical replicates, while these ones are called biological replicates. So the experimental unit is the biological replicate. It is the one where you change your treatment. So let's say that the treatment is applied to the animals, and these are technical replicates that we have seen that the right way of dealing with them is by averaging them. So technical replicates are very good to decrease the variance. We were talking about this before. So if you have more precise measurements, then you will have more power to identify small changes. So in summary, not all the experiments have to be done in the same way. So depending on the number of factors, you may want to use some and your objective. So if you want to compare different groups, then these randomized block designs or completely randomized designs are good. If you have a large number of factors and your objective is just to identify which ones are important, then this factorial, either full or fractional factorial, here if you have many factors, they are the ones. We haven't seen this placket bookmark, we will see along the course. And if your objective is to maximize the response, then you will use different kind of design. So not all the experiments have to be done in the same way. This is the main message. Here is another idea, that is you will need to calculate the sample size. So this Metz resource equation is a way of calculating it, So here you are separating number of treatments, number of blocks, number of degrees of freedom for the residual errors, and then total number of experimental units. It is recommended that this degrees of freedom is somewhere between 10 and 20. And overall, I would say this is a way of having a ballpark sample size calculation, but it is not the way it should be done. The way it should be done is a power analysis that you have a full course also on YouTube on this, and but it gives you an idea of how many animals you will need in total. So with this we finish, and we finish this first lecture, and then I'll see you in the next one.